greatest net force applied in order to hold something in a turn. Okay? Newton's first law does not allow that. It's not a natural state of motion. It's highly unnatural. We'll find that there's some very, very specific requirements for that force, or otherwise you'll fail. It's possible that you don't hug the turn enough, or it's possible you hug it too hard and you squash it. There's a just right Goldilocks amount of force that's needed. Now, before I tell you that, one thing that you may have noticed is I've drawn these two perpendicular, and I haven't really convinced you why it has to be perpendicular, and in fact it doesn't need to be perpendicular. All the arguments I made about nudging it to the side to maintain the turn, they don't hinge on it being perfectly perpendicular. So what would be so bad about if you had something like this? What would be so bad about nudging it to the left like this? That would still nudge it off its path. This force does still have a component to the left, so it would still make it curve to the left. What's wrong with that? Nothing really. I could break this force up into two components, one that's with the motion and one that is perpendicular to it. I'm going to label these components F tan, because it's along the same line as the velocity, so tangential to the circle as well, and FC. C stands for centripetal, and I'll write that down in just a second. So we could talk about the action of each of these force components on the velocity separately. It might even be nice to draw those separately like this. Oh, and I guess one of the things I could talk about is F tan causes A tan. FC causes AC, okay? So each component of the force causes its own acceleration as well. We, of course, normally do that with X and Y, but here I'm just calling the two components instead of X and Y, tan and C, okay? So what's so bad about having an A tan? What's so bad about having a force component and acceleration with the velocity? There's nothing wrong with it. In fact, we know exactly what this does. This was our one-dimensional stuff, right? What's going to happen to that? What's going to happen if your acceleration and velocity are in the same direction? You're going to speed up. So A tan is responsible for changes the speed, but you will be forever doomed to move along this axis. Okay? You will speed up or slow down, maybe go so far as to slow down, stop, and turn around, right, if A tan is opposite to motion, but you will be forever trapped on this line, right, this one-dimensional motion. So the direction of motion, aside from perhaps turning around, you're trapped on this axis, okay? So A tan is the old boring stuff, right? That's the speed change part. A centripetal has just the opposite effect. A centripetal, the force and acceleration that's centripetal, is what constantly nudges you off the axis you used to be on onto a new axis. Okay? So this does not have any effect on the speed, but it does change the direction. So you can see what we've done is we've kind of made this situation more digestible. Okay? So if we have a velocity, velocity has both speed and direction. Now what we've done is we've taken the thing that changes the velocity, acceleration, and we split it up into two convenient parts. the acceleration, we split it up into A-tan and AC. A-tan changes the speed, but doesn't affect the direction, and A centripetal is vice versa. So it's just a way to make it more digestible for us to look at, okay? So we like to think of the velocity as two pieces, speed and direction. We then also take the acceleration, which generally, of course, changes the velocity, and we like to break it into components so that each component of the acceleration operates on one thing about the velocity, the speed or the direction, okay? So, if you go back over to my original picture, what I've done here is I've drawn the F net so that it happens to be completely perpendicular. So this F net, as I've drawn it over here, if that can generally be thought of as a tangential component and a centripetal component, I have made the tangential component 0. Which means I have simply drawn the situation where you have a bare minimum of going in a circle, but you're not going to make it go faster or slower as you do that. Of course, it's perfectly possible to go in a circle and go faster or slower while you're doing that. But if I wanted to draw just the most basic circular motion, I have purposely drawn here what's the special case of what's called uniform circular motion. Uniform simply meaning constant speed. So that's where I'm nudging the path into a circle, but I'm not doing anything more than that. I'm not making it go faster or slower, okay? So what we will do for the time being is we won't really use the tangential component at all, okay? We'll throw it away. We'll introduce it later in the course when we not only talk about what does it take to go in a circle, but, oh, now you're speeding up or slowing down while you're doing it. So for right now, we're going to focus on this, okay? We'll come back later. This also brings you an interesting point here. This uniform circular motion is constant speed, but not constant velocity. That's a statement that you, perhaps before you got here, you wouldn't have understood the subtlety of it. You're saying, what? I mean, speed and velocity are kind of interchangeable, right? Well, just because it's going at constant speed doesn't mean it's going at constant velocity. Why isn't it constant velocity? Because the direction part of velocity is continuously changing when you're going in a circle, okay? So by virtue of going in a circle, you are accelerating. You have a very strange acceleration. It's not operating on the speed at all. It's not making it go faster or slower. The acceleration is accomplishing a completely different task. It's changing the direction of motion. So for instance, in a car, if you want to talk about things that accelerate your car, you have the gas and the brake, and what else? Steering wheel. When you turn your car steering wheel, you are accelerating your car, okay? Any change to the velocity, even changes to the direction of it, are requiring acceleration, because an object would never spontaneously change its own motion in any way. It wants to keep whatever speed and direction it has at the given moment forever, okay? All right, so the next question is, okay, we know that we need a force and acceleration. How much do we need? The answer is not always 5 newtons, okay? That's a one-size-fits-all. It's a little bit ridiculous, right? It's like the what's the meaning of life? What is it? Does anyone know? 42? Yeah. Is that right? Is that the right number? Okay. So that's obviously ridiculous, one-size-fits-all answer, okay? So we need to figure out what is the formula for how much force is needed in a particular situation. So I said I would write it down. Centripetal force. Okay. This is the force. This is the radially inward force required. Actually, let me just write it like this. This is the force required to go in a circle. We need to address the size. We need to address the direction. I'll put radially inward. How much is the force? Well, it'll be the mass times whatever acceleration is required. Now here's where I have to just pull something out of thin air. At least with this one, I think you'll be doing a lab to confirm this. The amount of acceleration required is v squared over r, meaning the force is mv squared over r. So the amount of force that is needed to hold your turn depends on how fast you're going, what radius of circle you want to make, and how much mass is it that you want to take. Okay, how much mass is being made to go in a circle. Now, what happens if you don't get that force? Of course, you will fail. You can fail in many ways. Let's take a look at the fails. If the actual amount of force is less than the required amount, you'll fly out. You will not be able to hold that circle. Of course, the extreme case of that is if you have no force at all, right? If you don't have any force, you can't hold a circle. You'll go in a straight line, which is certainly out away from the whatever center of circle you have. You can fail the other way. The actual amount of force pulling toward the center is too much. Then you hug it too tight. You will actually collapse the circle. You're pulling inward too much. It's only if the actual amount of force is exactly equal to the required, then you will maintain the amount, you will maintain the circle. Okay? So this is a very strange thing to wrap your head around. We have an object, it's moving in a circle, it's accelerating towards a point, the center of the circle, always. The acceleration always points to the center, toward the center of the circle, and yet you will never get any closer to it. You will accelerate forever towards a point, and yet never change your distance away. It really requires you to expand your ideas of what acceleration really means. Okay? Now, don't get me wrong. If you didn't apply that, didn't have that acceleration pointing toward the center of the circle, you would actually fly away from it. So you would go flying away from it. If you pulled too hard toward the center, you would not only accelerate toward the center, you would actually go closer to the center. But striking a balance between getting further from and getting closer to, we have this acceleration that exactly maintains your distance from the center of the circle. So it's basically just enough acceleration to keep you equidistant from the center, but not so much acceleration as to actually get you towards it. Okay? And let's take a look at what goes into this equation. This says that if you go faster, your centripetal force will increase. Okay? The faster you go, the more force is required. And remember, that's what centripetal is. When you hear centripetal, think required. Okay? So the faster you go, the more force is needed to hold the turn. Okay, so if you're driving when it's slippery out, you want to slow down. Why is that? Well, you don't want the force that's required to be too much. right? So if you want a safe driving here, you want to slow down. You want to slow down so that the required force isn't too much. You want to limit what you're asking for, because remember, just because you want it doesn't mean you get it, okay? You don't want your centripetal force, your required force, to be too large, because then of course the danger is that you can't get that much force, right? So you'll fly out. And you drive too fast, you'll fly out of the turn. Why is that again? It's because the actual amount of force wasn't enough to meet your requirements. There's only so much friction you can get from the road. So if you require a lot of force, that doesn't mean you get it. Okay? Going in a circle is a privilege, not a right. One of the other things you can do is mess around with radius. Okay? So if we wanted, again, let's talk safe driving. If we wanted to lower the centripetal force, well, what should we do to the radius? Should it be bigger or smaller? Bigger, right? If R is bigger, FC is smaller. So you should not only drive slower on slippery days, but you should take, so R has to be bigger, right? Sorry, R has to be bigger for FC to be smaller. So you want to take larger radius, more gradual turns. Okay? So that's another way that you can decrease how much force you're requiring, because if you ask for too much, you might not get it. So if it's been raining out, drive slower and try to take nice wide gradual turns. Don't just yank the steering wheel really fast. Okay? Because the tighter of a turn you want to make, the smaller radius of a turn you want to make, the more force it's going to require. And what you might happen is, again, what you require, the actual can't keep up with it and you'll fly out. Okay? And then of course mass as well. Smaller mass, well, smaller mass is less inertia, right? It's not as stubborn to changes. That's changes of any kind, even if you just want to change its direction. So if you want to drive as safe as possible, drive slow, take gradual turns. The mass term is a little bit weird for driving, because that also can affect how much friction you get. So better analogy would be that if you had like a mass that you wanted to swing around your head on a string, right? If you don't want to exceed the braking tension of the string, you should have a lower mass, right? Because a lower mass will not require as much force to hold it, okay? So those are the three things that enter in to how much force is needed to hold a turn. These are good for proportionalities, particularly the V. Notice that if you drive twice as fast, how much more force is needed to hold the turn? Four times. So you better hope that whatever is actually holding the turn can supply 4 times more force. If not, you're flying out. Okay? So that's basically the theory. And the one thing I do want to emphasize again is that this is just a requirement. Okay? You can use this formula to calculate how much force would be required to hold this mass and this turn at this radius and at this speed. That doesn't mean you actually get it, okay? So the actual forces that might be available might be smaller. You'll fly out. The actual forces acting might be bigger, in which case you'll fall in. And if you're lucky, the actual forces from the real world will meet this requirement exactly, okay? So remember that one or more real world forces, I guess I'll call them real world forces, must provide this. So things like tension, normal force, gravity, friction, those things have to be no more and no less than the requirement that you're asking them to meet. If they don't match with that, well, then you don't get to go in a circle, okay? So the common misconception, and I don't know what to do about this is just an eternal struggle. When people hear centripetal, they think, oh, it's another force to add to the list. Normal force, tension, friction, gravity, whatever. That's not what this is at all, okay? This is a label for a requirement. It's a force requirement, okay? It doesn't belong on that list, okay? So the forces we've looked at so far, tension, normal force, gravity, friction, those things can make objects do all sorts of things. They can make them go in a straight line, they can make them do whatever. But when you have a very specialized motion like circular motion, there is a formula which tells you exactly how much force is necessary to do that. And that's what this is, okay? So with that in mind, let's go ahead and do some examples. Are there any questions on the theory before we start doing that? Okay, so let's do some examples. First one, really basic, basically conceptual. I'm going to go out into deep space. And by deep space, I mean that the force of gravity from whatever distant masses can be neglected. And I'm going to take a bucket and I'm going to swing it. I'm going to attach it to a rope. The rope is perhaps attached to my spaceship, some kind of fixed point. And I'm going to give the rope a velocity. The speed of it is 1 meter per second. Let me say the mass of the bucket's 1 kilogram. Let me say the string's length is 2 meters. And so if we assume that the rope doesn't stretch or break, then obviously this thing won't be able to go in a straight line. It'll go in a circle. So let's talk about, first of all, how many forces act on the bucket, all right? So can anyone name me a force that acts on the bucket? Tension. Tension always pulls, never pushes, so tension will act like this. Any other forces that act on the bucket? What's that? Deep space, so no gravity. Also no friction or air resistance. No normal force, right? The bucket's not on a solid surface. Velocity is not a force. Okay. Anything else? That's it. One force. There is one force, and that one force, which is the tension, happens to be, by virtue of the fact that tension always pulls radially along a rope, that tension happens to be radially inward. So the tension is the centripetal force. The tension is providing the amount of force necessary to hold the turd. And that's good because the tension, of course, we take our ropes as being able to exert lots of different tensions. We usually neglect the breaking strengths, which means that whatever amount of tension is needed to be provided, this thing can provide. So the actual force, which is the tension, matches the requirement, and when you're going in a circle, the amount of force needed to hold the turn is mv squared over r. So we of course put this in. The length of the string also sets the radius of the circle. Plug it in, you have 0.5 newtons. Now that's pretty easy to compute, but let me show you a really common mistake that students make, and it sort of works sometimes and then it starts to really get them into trouble. Okay, this is where if you've never had physics, you're probably in better shape than if you've developed some bad habits. here's some erroneous thinking. I see this all the time. So a student looks at this and goes, aha, tension's down. But it's not moving down. So there's got to be like another force like this called the centripetal force. And then like these two cancel, and that's why it doesn't fall down, which is wrong on many, many levels. Okay? I mean, you get the same result. A lot of, you know, this equals this, but for this is like many wrongs make right. Okay? Because first of all, there's no force outward at all. Okay? And moreover, if there were two forces that canceled, this thing would have no net force. It would go out in a straight line. It wouldn't go in a circle. Okay? So wrong, 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 wrong. Okay? There is no outward force. Okay? There isn't a tension and a centripetal force. The tension is the centripetal force. Centripetal force is not another force. One or more forces step up to meet this obligation. And so what you do is you